Hi, this is the presentation for Group D in Computer Architecture. The group includes Russell Huai, Hai Cho, and myself, Kyrie Kutaba. Our advisor is Professor Mohammed El Hadidi, and we're covering the Advanced Encryption Standard. The proposal for this project is going to be an evaluation of the AES algorithm on the microblaze device, a Raspberry Pi, and 3 x86 or personal laptop or desktop computing devices. We're going to be looking at what AES is, which is the Advanced Encryption Standard, looking at the type of cipher it is. And this algorithm was adopted as the US Electronic Data Encryption Standard in 2001. And it uses a symmetric key algorithm, which I'll be talking about more in a few slides. We're also looking at performance over microblaze, which is a soft microprocessor core designed for the Xilinx FPGAs, which we're going to be looking at using the Nexus A7 board. The motivation for this project is that AES is the current standard for encryption and decryption in the United States, so it's very widely used. We want to look at how this encrypting process is, how it differs over multiple platforms that are also commonly used, like x86 personal computing devices and the Raspberry Pi and the Nexus FPGA 7 Nexus A7 board. We're going to be comparing and contrasting a few different performance metrics, including the cost of running AES, the speed on each device, and the power consumption to run the process. We're going to be looking at, lastly, I'll talk about how the algorithm itself works. The AES algorithm was adopted in 2001 after a long review process. It's based off of the Richendale algorithm, which is a symmetric block cipher. That means that the same key used to encrypt data as it comes in is also used to decrypt data on the back end. This is going to be using in either 128, 192, or 256-bit key size, with a higher bit size representing a more complex algorithm. The 128-bit is most commonly used today and is fairly secure. There haven't been many successful brute force hackings. The encryption and decryption rounds depend on the key size. The lower 128-bit key size calls for 10 encryption rounds. In each round of encrypting, there's a sub-bytes operation where bytes in the state are transformed to other bytes. There's a shift rows operation where the last 3 rows of the state are shifted to the left. And there's a mix columns operation where each byte in the state is replaced with another column. And lastly, there's an add round key, which adds a round key to the end of each state. And this operation takes place in every round of encryption besides the last round. And since this is a symmetric block cipher, the same key can be used to do this process. When we decrypt, we just use the inverse of each of these processes.
So I'm going now to talk about the platform. We are using 3 different devices: the microblade, the Raspberry Pi 3B, and the x86 CPUs. For the microblade is soft processor by ceiling that intended to be used for FPGA. They are extremely configurable with memory I/O cage. They can be programmed with FlightDisk, configured and built with hardware on Vivato's. For the Raspberry Pi 3B is running a RISC ARM BCM2837 64-bit CPU and with 1 GB of RAM. It's running a 32-bit version of Raspbian OS. For the x86 CPUs, we're using 3 different devices. They are Intel Core i5-1200F, the desktop CPU, and Intel 9300H laptop CPU, and the AMD Ryzen 4600U laptop CPU. Next, I'm going to talk about the methodology, how we measure the execution and the war time. So that to do that, we're using a time.h class, and there's the viewing time star and the start clock. By putting those 2 variables at the beginning of the program and pushing the the other two variable at the end of program, we are able to measure the CPU time and the wall time. So for instance, for the CPU time, which is just the difference between the end clock and the start clock divided by clock per second. For the wall time, it's just a difference between the time end and the time start. So next is I'm going to explain how we measure the power of the x86 CPU. To do this, we are using a program called XW64infos. This is a program to measure a wide range of different sensors in the computer. So what we're doing is we start a recording of the XW64infos program, and then we time the moment that we start the program. We just taking the current time. As you can see right here, the first time is 305 seconds. This is idle state of the CPU. And at this instant of it go up to 307 seconds, the CPU spike up to 21. And the difference between those is the power consumption of a TinyAES program on the x86 CPU. So for the Raspberry Pi, what we did is we measure the power using the USB digital tester, this device. And you can see here, right here, we just measure the idle state of the Raspberry Pi. And then we run the program and we measure the power. You can see here, the difference between the two is 1415 watt and 145 watt. For the methodology, since the time.h is not available on Vitis, so we can only measure the wall time. What we're doing is we're printing a simple start and end program statement with all the codes, and then at the end of the code, what it does is output like a statement on the term. It's allow us to see whether the program is running or not, and we're just using the digital power tester to measure the power, the idle state and the active power state. And now Russell is going to talk about more about the performance evaluation.
So as you can see here, we have the power consumption for optimized code. As you can see, the desktop CPUs 12400F and the 4600, they have a lot more power consumption compared to the Raspberry Pi and FPGA. And here we have a chart for the performance comparing the optimized and unoptimized code. As you can see in the red versus blue, we have a big performance gap, indicating a big performance improvement from optimized and unoptimized. And as you can see, the desktop CPUs are much faster. And here we have the performance versus cost, basically the value of each system. As you can see, the desktop CPUs actually have a lot of value compared to the Raspberry Pi 3B and the FPGA, which is a lot less value. We also have the idle versus full load for power usage. As you can see, the desktop CPUs again, 1200F and 4600, they use a lot more power, both during full load and during idle. Compared to the Raspberry Pi and the FPGA here, especially FPGA, there's not a big difference. In fact, there's no difference between the power usage on idle compared to full load. In the case, it doesn't have any power saving during idle compared to the other systems. So in conclusion, enabling optimizations greatly improves the performance of the code. The FPGA is quite expensive and slow, but it is highly reconfigurable. The Raspberry Pi is low power, low cost. It's slower, but it's still usable compared to the FPGA. For x86 or the desktop CPUs, they have the most performance with especially with hardware acceleration, but they have a higher cost and a lot higher power consumption. So basically, you want to choose a platform based on the needs, whether it be power, cost, and performance. And basically, optimizations make things go a lot faster. The FPGA is very expensive, but it's very reconfigurable, which none of the other systems have. The Raspberry Pi targets low power. The PC targets performance, especially with the hardware acceleration. That concludes our presentation.